Good afternoon, everyone. Thank you for coming to this afternoon's event, jointly sponsored by the Assembly Series and the Weidenbaum Center. I'm Steve Smith, the director of the Weidenbaum Center and a professor of political science here at WashU. We are here today to learn more about new developments in the science of climate change, and it's really a special pleasure to have Dr. David Easterling here with us today. You know, I can't help but notice that President Trump issued an executive order this afternoon that did a few things related to this afternoon's subject, instructing federal agencies to rewrite the rules on carbon emissions, undoing the moratorium on leasing federal lands to the coal companies, and removing the requirement that federal officials account for the effects of their policies on climate change. And they're also considering, of course, soon to reconsider the vehicle fuel efficiency standards. So there's an awful lot of activity happening. I'm one of those who think that the best way to address these issues is to continue to learn the facts about climate change and to consider our policy options for addressing it. With that in mind, we have David Easterling here today. Dr. Easterling's degree is from University of North Carolina. He served on the faculty at Indiana University before moving to the National Oceanographic and Atmospheric Administration back in the early 90s. He's now the director of the National Climate Assessment Technical Support Unit of the National Centers for Environmental Information, which was previously just recently formed as a combination of several agencies under NOAA, including the National Climatic Data Center. He's located in Asheville. He is the author of many important scientific publications in all the major scientific journals, and a contributor and author to all of the recent reports of the Intergovernmental Panel on Climate Change. With that background, we couldn't have someone more expert to address new developments in the science of climate change. And I hope you all join me in welcoming David Easterling to WashU.
Thank you for that introduction. I never thought I'd actually be in a courtroom giving a talk like this, but can you guys hear me okay? All right. Let me, is that all right? Okay. How's that? Okay. So like I said, I never thought I'd be in a courtroom giving a talk like this, although I know some scientists that keep saying that someday you're going to end up in a courtroom testifying about climate change. So what I would like to do today is to basically go over the scientific basis for climate change. As you heard, I am at the National Centers for Environmental Information in Asheville, North Carolina. Used to be the National Climatic Data Center, and so I'm a climate scientist. We had a merger of the National Oceanographic Data Center, which is in Silver Spring, and the Geophysical Data Center, which is in Boulder, Colorado, into what we call now the National Centers for Environmental Information. So I want to give you just a little background on where I come from, and then we'll get into the science of climate change. And by the way, I like to wander around, and if you've got questions that you're just burning to ask before the end of the talk, please raise your hand and I'll be glad to answer it. So, make sure. So, we are the world's largest archive of weather and climate and geophysical and oceanographic data. We have data from radars, from the oceans, tree rings, for proxies, for reconstructing climate before we had instruments. We get it from ships, ice cores, and this is one of our really high-end observing climate stations. We have about 120 of these around the country that we actually started at our center to try to track the climate of the U.S. a lot better. We store all these at the center there in Asheville, and this gives you an idea of the size of our archive. Starting in 2000, we were way down at about maybe 1 or 2 petabytes. So if you, and I think I get this right, you go mega, tera, giga, no, mega, giga, tera, peta. So it's a lot of data, and this sort of is supposed to give you an idea. 24 petabytes is storage in a stack of iPhones. I don't know if those are iPhone 5s or 6s, but 16 Eiffel Towers high. So anyway, it's a lot of data. Most of that is satellite data and radar data, because those can produce a heck of a lot of data. But we also have observations of climate from all around the world. We have both land-based, so these are temperature and precipitation records and pressure and clouds and that sort of thing. And we also have oceanographic data. The most important as far as climate for us right now is the temperature data, both the sea surface data and then also the deep ocean data, as well as ocean salinity, acidity, and things like that. So we, at Asheville, we monitor and assess the Earth's climate, and we do a lot of reporting. We do things like wildfire, harmful algal bloom observing systems. One of the big things that we do is every month and then annually we put out a state of the climate report that basically tracks what happened either the last month or the last year, and try to place that into historical perspective, because that's where we begin looking at the long-term trends. Okay, so without further ado, let's jump into climate change and what's the evidence. Okay, just a little background, weather versus climate. So weather is sort of the local, short-term. It can change day to day, hour to hour. That's why when you saw some politicians with snowballs in Congress saying, oh, you know, where's your global warming now because we had a snowstorm? Well, so what? I mean, with long-term climate change, you're still going to get snowstorms. You're still going to get cold weather, just maybe not as much or not as severe. Climate, though, is the sort of what the weather is normally like year to year, decade to decade. Usually we measure it over periods of about 30 years. Basically, the climate tells you what clothes to buy and have in your wardrobe, but then weather tells you whether to wear shorts or long pants that day, whether it's too warm or not. Okay, so what's the evidence? This is something that we produce in Asheville. We produce every month and annually, and it is the globally averaged surface temperature. So if you were to take observations from all around the world, both land-based and ocean-based, so these are sea surface temperatures, as well as temperatures that are measured at observing stations, and we average them all up into one number, this is what you get. And this starts in 1880. That's about when we had enough instrumental data to be able to begin monitoring the Earth's climate. And as you can see, we had from 1880 to about 1910 or so, it looked like it cooled a little bit. And then since then, with the exception of here in the 1940s, and really just this one spike right here of about 6 or 7 years, it's been warming pretty rapidly. And if you look at the period from about 1970 to the present, you can see we've had this very rapid warming, and that actually coincides with the fairly rapid increase in greenhouse gases that we've seen and measured at various measuring sites all around the world. Okay, where was it warm last year? So, just back up. One other point. So if you see these last 3 years right here, okay, this is 2016, 15, and 14, each year was a record, was warmer than the previous year. And the only other time that we actually have that was back here in the late 1930s, early 1940s, okay? And some of you may have heard the term hiatus in the global temperatures. Okay, and I'll talk about that in a few minutes. Well, this is what we're talking about. It's a sort of, kind of flattening out in the global temperatures. But the last 3 years have pretty much put a nail into that notion that we've had a pause in warming. Okay, and again, I'll talk about that in a few minutes. I'm sorry?
That abnormal warming?
That's actually a really good question, and partly we think is kind of a data problem because that was the start of World War II. And remember that 70% of the world's land area is ocean, or surface area is ocean. And so we think part of it is because we don't have a lot of data that was because of ships. So the sea surface temperatures that we get are from ships of opportunity. So freighters, Navy ships, they all take sea surface temperatures. they'll drop a bucket over the side and bring it up and then stick a thermometer in it and then put it into their ship's log. And part of that we think is due to just not enough coverage to be able to get a really accurate picture of what was going on. But beyond that, you know, the climate has natural variability as well as its long-term trend, okay? And so if you look at climate models, for example, what you usually see, and I'll show you a little bit, it's just smoothly varying time increase in temperatures, but what's lost on that is the fact that we have year-to-year variability. And you see this in this one, you know, you see the stair-stepping. You know, this is 1998 right here, and that's when we had a very, very strong El Nino. Okay? El Nino is unusual warming in the tropical East Pacific ocean temperatures. And when you have a large area of the Pacific Ocean like that with very warm sea surface temperatures, it can impact the total global temperature to the point that we had the spike. And that's what started this notion of a hiatus, was if you fit a temperature trend from here to about here, which is when it first came out, and people started first postulating this hiatus, then you would get very little trend. Okay, but just keep in mind there is natural variability. You get these ups and downs, but you can see also that we have this long-term trend, and if you just fit a simple trend line, you get a fairly strong warming there.
Average of this period, so that this might actually be warmer
Yes.
than the previous.
That's a good point. This zero line is simply the long-term average of this period.
I'd like
Okay.
some time. The audience, so there'll be plenty of time for question and answers and presentations.
Okay. So, and these are what we call anomalies. These are simply differences from the long-term mean. That's why it goes zero, it goes negative on this side and positive on this side. So instead of simply putting up, you know, the globally averaged air temperature, which is, that mean is about 58 degrees Fahrenheit, we simply work in anomaly space because that's how we actually have to create these big average temperatures, is we have to subtract the mean from the observation and then average them all up. So that's why you get this. Instead of that being 58 degrees, is zero. Okay, so 2016 was the warmest year on record. 15 was the previous record. So just give you an idea of where it was warm in 2016. Okay, so this is the warming. This is the period respected to this base period here. So it would be an average over this, and you subtract that, and you come up with where was it warm, where was it cold. So you can see it was warm pretty much everywhere, with the exception of these blues. So where it's red and pink is where it's warm. Where it's blue was where it was unusually cold or cooler. So if you look at Alaska, for example, it was very warm up there in 2016. Also in the higher latitudes of Russia, but also into Canada and even in the northern part of the US, it was unusually warm. We had a few pockets here and there, and this is actually a very interesting spot because this is one of the few places that actually shows a long-term cooling trend, okay? Remember, climate change is not going to be exactly the same everywhere. It's not going to go up 3 degrees everywhere on Earth. It's going to be different depending on where you are. We expect the greatest warming to occur at the highest latitudes, and that's what this map is. Okay, where has it warmed? And these are trends from 1901 to 2015. And you can see the darkest reds generally are in the higher latitudes. In some places we don't have good data. That's why it's grayed out. But in general, we're seeing the greatest warming in the highest latitudes. Okay? And that is partially due to what we call a feedback in the climate system, where you begin, if you look at snow cover, for example, you begin looking at snow cover trends through time. We're seeing a reduction in that. And as you reduce the amount of snow cover, and especially as you reduce the amount of sea ice you have in the Arctic, for example. Remember, the Arctic, all this area up here is ocean. Okay, it's covered by sea ice generally in the wintertime, but I'll show you some satellite images a little bit later that shows you that Arctic sea ice is reducing drastically. In the middle of winter, it's typically covered anyway, but where you really see the differences in the summertime, and especially in September, where you have a minimum of sea ice, you're seeing very drastic reductions in sea ice. Well, as you reduce the amount of sea ice up there, you have more exposed water. So sea ice and snow reflect sunlight. Open ocean tends to absorb it, and so you get warming simply because you're having more open ocean and less sea ice. So you can see that the warming has been the greatest, and keep this little area in the U.S. and the southeast in mind, and this area right here. And when I show you a little more detail, especially in the U.S., you'll see that there's a little bit of cooling over this period in the southeastern U.S., and it's what we call the warming hole. And it's a subject of research that we're trying to figure out just why we're seeing in that one little area in the world there and off the coast of Greenland, we're seeing a little bit of cooling. Everywhere else is warming. Okay, so that's what we call surface temperature. So basically that's either observations taken at about 5 feet in temperature shelters, or it's ocean temperatures, ocean sea surface temperatures. Another way that we look at the climate and whether it's warming is using satellites. And there's a satellite that gives you a temperature that's an average across a layer of air in the troposphere. So the troposphere is basically from the Earth's surface up to about 20,000 feet. Okay, it's what we call the weather sphere, is where most of the weather occurs. And what we want to do is, okay, it's warming at the surface. Well, what's it doing higher up in the atmosphere? Is it warming or cooling? And so we have satellite measurements that we could use to look at what's going on in the troposphere. Okay, we only have these from 1979 to the present, and this is two different versions. One from the University of Alabama at Huntsville, and another one from a company in California called Remote Sensing Systems. And basically what they do is they take all the satellite data for this layer of air that's about, for this one, this is the mid-troposphere, or lower troposphere, and so it's from somewhere around, say, 6,000 feet to about 12,000 feet. So you're looking at a temperature average across that layer of air, and what do you get? You do get warming. Okay, so this is from 1979 to the present, a lot of up and down. You see there's some separation between these two records, okay? And the reason is satellites last, they're very expensive, but they only last about 5 to 8 years. And then you gotta put a new one up, and you have to have an overlap. Okay, so you put, let's say, NOAA 5 up, and it's up there for a while, and then you put NOAA 6 up, so there's some overlap. But these satellites degrade over time because they gradually sink. Gravity gradually kind of pulls them towards the Earth's surface, and then also these are what we call polar orbiters. So they basically rotate, or they orbit from pole to pole, and the Earth then spins underneath them, and they're able to measure what's going on twice a day at any given location. Well, what happens is the time they cross the equator gradually shifts as well. So all these things, where I'm going with this is all these things have to be adjusted for, and all these records have to be put together. So you got NOAA 5, NOAA 6, NOAA 7. These are different satellites. And so this is a record that's composed of satellites, probably about 6 or 7 satellites. Okay, but the bottom line is they also do show warming in this layer. Okay, they did diverge a little bit because they're processed different ways to account for some of these issues with orbiting, with the orbits. But the bottom line is they gradually come together. Now, 2016, even the satellite record for this troposphere is also the warmest year on record. It used to be 1998. But now, even 2016, and the satellite record is now the warmest year on record. Okay, so the hiatus, I mentioned that a little bit earlier. Was there a hiatus? So this oval right here shows you the time period we're talking about, 1998 to somewhere around 2013. Okay, a lot of the I hate to use the term skeptic or denier, but a lot of people in that sort of community have seized on the notion that global warming had stopped. Okay, from 1998, if you were to fit a trend line right along in here, you would get very little or no trend, which you shouldn't do it anyway statistically because you don't have a very long period. But the bottom line is they were saying, well, look, global warming is not an issue because it stopped. Well, clearly, 2014, 15, and 16 have resumed warming. So that really, in my mind, is not really an issue. But we also, in our data center, we produce this data set that is used to produce this curve. And one of the things we have to do is to make certain adjustments for the fact that we have a mix of observing systems. We have satellites, we have ships that drop buckets in, we have ships that take temperatures from the cooling water intake, we have buoys and different kinds of drifters and things like that. And you always have to make sure they're coming from the same baseline when you put them together. So we've done a number of papers looking at the so-called hiatus. I did one back in 2009 that just said, if there's a hiatus or not, if it's not a big deal because you see these in the observed record all the time anyway. But a couple more, and this one actually, that came out in Science last year, caused quite a ruckus in a lot of areas, not the least of which was Congress, because this one showed that it was actually this so-called hiatus was an artifact of the way we adjusted our data, and when we did it properly, that it went away. So a new version of ours shows no hiatus, and we had new corrections for drifting buoys. So buoys measure about that much below the surface, so it's about 1.5 feet or 2 feet below the surface. Others measure actually right at the surface. So there's a difference between what you're measuring here and what you're measuring up here, and you have to actually account for that. And when we accounted for that the right way, we found that lo and behold, between that and adding more land surface temperature data than had been previously available, the hiatus went away, okay, in our data set, okay, but it did cause a lot of consternation, we'll put it that way, with some people in Congress. And we actually had another very independent group that replicated our work. And what's interesting about this group, Zeke Housefather and some others at Berkeley, they started off as a group that said, there's like 4 groups that do the global temperatures, like I showed you right at the beginning. Okay, there's us, there's a group in Great Britain, NASA Goddard up in New York, and then now this group that's out at Berkeley, and they started off saying, well, they didn't think we were doing it right. Okay, they thought they could do a better job, and I think they originally thought when they did their better job that they would get different results than what we got, and it turns out they didn't. And this is actually from their paper that was looking at the way that we adjusted the buoy data to come up with the fact that there was no hiatus. And they said, nope, they're right. You know, they're doing it right. So it's always nice when you have a group that starts off saying we're going to contradict you, that they turn around and say, no, you're doing a good job. Okay, so we've established to a large extent that it's warming, and I'll show you some other evidence because I'll admit I'm a scientist, I'm a little bit of a skeptic, and if it was only the temperature record that we were looking at and there was no other lines of evidence showing that it's warming, I'd be a little more skeptical than I am, a little less convinced. So let's take a look at why it's warming. Could be the sun, because that's where the energy comes from, and it could be stuff in the atmosphere. Okay, and we'll talk about that. So let's just a little basics on the greenhouse effect so everybody knows where we're coming from. So first off, without a natural greenhouse effect, Earth's average temperature would be close to 0. It actually would have wild swings if we didn't have an atmosphere. It'd be much like the moon. You know, it would go from hundreds of degrees to way below 0 because you wouldn't have any atmosphere that would actually keep the heat energy and keep the temperatures up at around 58 degrees Fahrenheit, which is what it currently is. So if you averaged temperatures all over the Earth, surface air temperature and sea surface temperature, you get about 58 degrees Fahrenheit. Okay, so a little basics on the greenhouse effect. So the energy source, of course, for the atmosphere, for the Earth is the sun. So we have sunlight coming in. Okay, most of the radiation, solar radiation passes through a clear atmosphere. Some of it actually is reflected back by the atmosphere, by clouds, by particulates in the atmosphere, stuff, like sulfur particles in the atmosphere. Those actually reflect back some of the incoming solar radiation. So we have, and energy coming in. Some is reflected by the Earth's surface, like snow, depending on how it hits water, how it hits some kinds of land surface, is reflected straight back out to space. But a large portion of it actually is absorbed by the Earth's surface and warms it. So the atmosphere is actually heated from below to a large extent. A little bit is, you get some absorption by ozone in the stratosphere that warms it a little bit and things like that. But in general, the Earth is heated from below. So if we're getting all this energy coming in from the sun, in order to maintain more or less a 58-degree Fahrenheit temperature, you also have to give off energy, okay? Because if you're just getting all this energy coming in from the sun and it's just being absorbed by the Earth's surface, it eventually heats up, okay? So you have to get rid of it somehow, and you get rid of it mainly through infrared radiation emission. So this is shortwave radiation or visible light, okay? And then some ultraviolet coming in, and then others like gamma rays and the very short wavelength radiation. But you got to get rid of it somehow, and you get rid of it because any substance that has a temperature above absolute zero, which is minus 273 degrees Celsius, gives off some energy, and it gives off radiant energy. Okay, for the Earth, it's what we call long wave or infrared radiation. Okay, so we have infrared radiation being emitted back up. And if you have an energy balance, which keeps, over the long term, keeps the Earth more or less about the same temperature, then the amount of energy coming in here is going to be offset and balanced by the amount of energy that eventually makes it back out to space by infrared radiation. So the greenhouse effect is actually right in here. Okay, and greenhouse gases absorb infrared radiation. So carbon dioxide, methane, nitrous oxides, ozone, all these absorb infrared radiation in some wavelength, and then once it's absorbed, then some of it's re-radiated back down to the Earth, and it keeps the Earth warmer than it normally would be. Okay, so that's the greenhouse effect. Okay, and we have a natural greenhouse effect, so the real concern is the fact that we have these greenhouse gases that are in this part right here that are absorbing this energy and then keeping it warmer are increasing. Okay, and they're increasing due to human emissions of greenhouse gases, mainly. Okay, so that's basically, that's the big concern is right in here, is where carbon dioxide and methane and other greenhouse gases absorb this energy coming off the Earth's surface and re-radiate it back down to the Earth and keep temperatures even warmer. So basically, some of this energy is actually being absorbed and blocked just a little bit and re-radiated back down. So that's where the big issue is. We have a natural greenhouse effect, but we're enhancing the greenhouse effect by increasing the amount of greenhouse gases in the atmosphere. Okay, what about aerosols? I mentioned sulfate aerosols. This is Mount Pinatubo. If you remember, that went off in the Philippines in 1992. Okay, and this is actually a satellite image showing the ash and sulfate aerosols and everything in the atmosphere soon after the eruption. Well, probably 6 months or so after the eruption. And you can see that there would appear to be a whole lot of it in there, and it actually did impact the climate because all this stuff right here, when it gets up into the upper atmosphere, reflects some of that incoming energy from the sun and caused global temperatures to cool somewhat. And that's what this shows. So this is the global temperatures, and this is a small segment of that longer time series I showed you earlier that shows the short-term cooling. That's when Mount Pinatubo erupted right here in 1991. And so for about 1.5 years to 2 years after that, we did have a little bit of cooling due to the fact that we had all this debris and sulfate aerosols and everything else that was injected in the atmosphere. The other source of sulfate aerosols is from coal-burning power plants. And so as we reduce our emissions of sulfates from coal-burning power plants, we're actually enhancing the greenhouse effect just a little bit. Okay, what about the sun's energy? Some people have speculated that the sun is getting more energetic, and so that's the reason why we're seeing warming. Here we have from late 19th. So one thing about measuring the energy from the sun, most of what prior to the 1979, most of it was sort of reconstructed from either proxies, so different ways that would indicate how much energy is coming in from the sun, or we had not a very good network of measurements around the Earth's surface. And so since 1979, though, we've actually had satellites that are out there looking back at the sun, and we get a very good idea of what the sun's variations in energy are like, and that's what this shows you. So here we have these spikes are sort of the individual observations, and then this curve is simply a smooth long-term average to show you that here we have cycles, okay, and there is no trend. If anything, there's a slight decrease in the amount of energy we're getting from the sun since the late 1970s, yet here's again, the global surface temperature that I showed earlier, and it's going up at the same time. Okay, this is carbon dioxide starting 10,000 years ago to the present, and this little inset is basically the start of the Industrial Revolution to the present. So you can see that starting somewhere around 5,000 years ago, we had a slight increase. It probably due to land use change, farming and that sort of thing, where you have slash and burn farming and putting whatever, burning whatever carbon is locked up in the plants that they're burning. And so we have this gradual increase, but here at the start of the Industrial Revolution, we were about 270 parts per million by volume of carbon dioxide in the atmosphere, okay? And so that's the sort of the pre-industrial level. And then if we look at recently what's going on, and these are two other greenhouse gases, nitrous oxides and methane, but this is sort of the iconic, call it the Keeling curve, for David Keeling at Scripps, who started measuring it at Mauna Loa. This is at our observatory. We have a NOAA observatory on top of Mauna Loa at about 11,000 feet. So we're up above the trade winds, and so we're really up in the free atmosphere, so we can measure sort of what's going on in the background as opposed to local sources of carbon dioxide. And so this started in the late 1950s, and you can see the stair stepping, which is just mainly the northern hemisphere green up and losing leaves and stuff like that. But you see that there's been this unrelenting increase in the measurements of carbon dioxide. And it's not just at Mauna Loa. We now have observatories at Barrow, Point Barrow in Alaska. The Russians have one. We have them in the southern hemisphere. They all show basically the same thing, that carbon dioxide has been increasing since the 1950s, and it has now gone over 400 parts per million, which is sort of an iconic level. It doesn't really mean much scientifically, but it is sort of an important thing if you're looking at, how we're going to reduce emissions. Methane has been going up. It does have more variability, and we had a little bit of leveling off from the 1990s to about 2005, but it's been going up again. Nitrous oxides is another greenhouse gas, also been going up. So all the major greenhouses have been increasing, and between that curve and the one that I showed you earlier with a very long-term view, you can see that we've increased carbon dioxide in the atmosphere by more than, not quite double, but getting pretty close since the start of, since about 10,000 years ago. Okay, so what other indicators of climate change do we have? Okay, this is a nice little infographic that just shows you the consistency with different parts of the climate system that we measure and whether they're changing in the direction that we expect them to change. And if you look at them, all the indicators expected to increase are increasing, and those expected to decrease are decreasing. So air temperature near the surface is going up. Water vapor, I didn't mention that, but water vapor is going up, probably a direct response to the fact that we're seeing warming, because as the atmosphere warms up, it can hold more moisture, and we're seeing that in the observed record. Climate models indicate that as temperature goes up, we'll see a lot more water vapor in the atmosphere, which can then lead to more extreme rainfall events. Temperatures over the oceans are going up. Sea level is going up, and I'll show you a curve in a few minutes. Sea surface temperature is going up. Ocean heat content, so that's below the surface, so from the surface down to about 700 meters, that's going up. Sea ice is going down. snow cover is going down, and glaciers, alpine glaciers, are retreating. And I'll show you some evidence for most of these. Okay, this is a really striking couple of photographs right here. This is Muir Glacier in 1941, and from the exact same location in 2004. And it looks pretty much the same in 2016. You can see in 1941, ice went all the way down. This is the, I guess there's a fjord there. This is the ocean right here. And so basically it's retreated all the way back up to here. Okay, and it's not just Muir Glacier, it's many, many, many glaciers around the world that we have the same thing. There are even paintings in Switzerland of where you've got the terminus of a glacier right next to a building or a church or something, and then now it's way back up the valley. Okay, ice loss from the two major polar ice sheets, the Greenland ice sheet. This is ice mass. Okay, and so this is how much ice is locked up in the ice sheet. And you see a decline. This is in 2002 to the present. You see the same thing in Antarctica. We're beginning to see a decline also over the same period. So we're losing ice mass. And if that's not floating, okay, if that's not ice that's actually on the ocean, that's got to contribute to sea level rise. Okay. Arctic sea ice decline. So this is, so I mentioned September is when you see the minimum in Arctic sea ice cover. Okay, remember this is an ocean up here. And so this is, it's September 14 of 1984. This is satellite based, so that's why it starts at about 1979. You can see in 1984, the minimum, this was the minimum here. Okay, and it actually was all interspersed in all these islands now. If you look at 2012, and if I showed you 13 to 14, it'd look very similar, even smaller. You can see now, you can drive a ship through there, and it's been done. Okay, I think it was a Norwegian freighter actually went from somewhere over on the west coast and all the way over to Europe through the so-called Northwest Passage. Okay. I mean, I guess that's a pro if you're looking for reducing shipping costs from Europe to Asia and back. But it has a lot of major issues for all sorts of other things going on in the Arctic. Not the least of which, there was actually a paper that just came out in Science that was looking at extreme events and linking the jet stream and meanders in the jet stream with Arctic sea ice reduction. Okay, so all this, actually, the Arctic sea ice is not going to increase sea level rise. It's already floating. But coming off of Antarctica and Greenland, because that's land-based ice, as it melts, it goes into the ocean and is increasing sea level. Okay, and this is the observed record. So we have proxy records starting about 1800, where people have taken things that indicate sea level rise and reconstruct it. This is tide gauge data. Here in blue, and then we have satellite data at the end in green. And we can see this gradual increase, and since 1800, it's gone up about 8 inches. It doesn't sound like a whole lot, but we are beginning to see impacts with it. So we have what we call nuisance flooding along the coast in the US that we measure. Okay, nuisance flooding it's not something that's going to cause catastrophic loss of life or anything, but it's just, you know, if you look at pictures of Miami where you got a car and there's about that much water on the street that's coming from high tides, that's what we call nuisance flooding. Okay, we're starting to see increases in the last couple of decades in the occurrence of nuisance flooding in places like Miami and Baltimore and Wilmington, North Carolina, Charleston, places like that. So it's a nuisance, and I'll show you what the projections are in a few minutes when we get into projections, but it's not pretty. So I want to jump to what's going on in the US. That was more of a global view, and what we're going to do now is to look at some of the results from the third National Climate Assessment, which is what I've been spending a lot of my life doing the last 5 or 6 years. So just a little background on the National Climate Assessment. So the 1990 Global Change Research Act that was under the first President Bush, so this was actually a Republican initiative, said you will do a climate change assessment every 4 years that looks at the impact of climate change on the U.S., what's going on with the climate. And so it took us, so it's supposed to be done every 4 years, and I was on the first one, and that didn't come out until 2000. So it took us 10 years for the first one. The next one came out in 2009, so it took us 9 years for the second one. And then the third one came out in 2014, so we're closing that gap. And the fourth one is supposed to come out in 2018. So what it does is it looks both at the evidence for climate change, what's going on in the climate system, but then also how that impacts various sectors such as agriculture and energy, water resources, human health. We just had a big assessment on human health come out last summer, looking at climate change and human health in the U.S. So what I want to do is to look a little bit at some of the results from the report that came out a couple years ago. Okay, report finding 1, global climate is changing, and it is apparent across the U.S. in a wide range of observations. And secondly, global warming in the past 50 years is primarily due to human activities, predominantly the burning of fossil fuels. Okay. Okay, this is observed temperature change in the U.S. This is something that we do at we have all the observations, we do at our center. This shows you by region. The National Climate Assessment was done by region. So we have the Northeast, Midwest, Great Plains North and South, Southwest, Hawaii, Northwest, and Alaska. And you can see everywhere it's red is where it's warmed over this period. Okay? And there's this one little area right in here and a little bit right in there that shows a little bit of cooling. Okay, why? We're actually doing some studies trying to figure out why you would see cooling in the face of everywhere else showing warming. We think it may be due to sulfate aerosols. Remember I said sulfate aerosols from burning of fossil fuels actually cools the climate, reflects some of the incoming solar radiation back. There were a lot of power plants and emissions in this area back in the 30s and 40s and 50s. It could be that. It could be something else. We haven't really ever nailed that down. But I can tell you the one thing is, if you look at, this is the time series for this area right here, and so it warmed to the 1930s. Okay, it cooled off to the 1960s, but it's been gradually warming ever since. Okay, and so even if we don't figure out why right now it shows cooling, it is turning around and beginning to show warming even in this area. So this blue is not nearly as intense as it was a decade ago. It showed a lot more cooling a decade ago. But if you look at it almost everywhere else, it shows warming, and this is the U.S. average, and you can see it's red pretty much everywhere, and especially in the northern plains and in the western part of the country and the Northeast. Okay, this is precipitation, looking at the same thing, and the one thing to note is a lot more variable. Precipitation is not going to change in the same way that temperature does. Temperature we expect more or less to go up some everywhere, more so in the higher latitudes, less so in the tropics, but we expect it to warm because greenhouse gases are pretty well mixed. But precipitation, you can see that some areas are drying. This is the Southwest, a little bit over here in North Carolina and Florida. But some areas show a lot of increases. The greens are increases and the browns are decreases over this period. And what that does show you that it's much more variable in what we expect to happen. And we do expect precipitation to increase at higher latitudes and decrease in what we call the subtropics. And so we do see this evidence here and here and here in the U.S. But there are some areas that even show increases over this period in precipitation. But what's more important than just an increase in the annual precipitation is extreme events. Okay, this is what really drives impacts to a large extent, are extreme events. If you get a gradual warming, yeah, you'll pass some thresholds and begin to see some impacts, but it's the extremes that really begin to matter. And this is something that we've done a lot of at our center, and I've done a lot of in my career, is looking at trends in heavy precipitation events. Okay, and when I say here heavy precipitation events, we measure precipitation taking 24-hour, once a day. Okay? So we take an observation. That's how much precipitation fell in the previous 24 hours. So these are 24-hour extremes, and we're seeing large increases in the number of heavy events in the U.S. Okay, this is 1900s all the way to the present, and we actually had a decline. Well, remember, that was when we had the Dust Bowl. So we had major droughts in large parts of the country. But since then, and especially in the eastern part of the country, we've seen some pretty large increases in these heavy rainfall events. And those do have impacts. I get asked by city water planners and people like that all the time, can you tell me what's going to happen to heavy rainfall events in the future? Because I'm planning civil engineering structures that are supposed to last for 50 to 100 years. Okay, how do I build them? Do I build them with more capacity or not? Can you tell me? And it's a tough question to answer. It's one we're actually looking at for the Department of Defense. And we have a project with them. But what we're trying to do is see, are these trends going to continue? Okay, this shows you where we're seeing these increases. The Northeast is seeing the largest increases. And then the Midwest and the Southeast. And gradually, as you get further west, actually, you remember this is drying in the annual precipitation, but we are still seeing a slight increase in the number of these heavier events. And that may be partially due to the fact that we're also seeing increases in water vapor over this whole time period. We are seeing a decline, actually, in Hawaii, in the tropics, but generally everywhere else, including Alaska, we're seeing an increase in these heavy events. Okay, what about hurricanes? Not a huge issue here, but it certainly is for large parts of the country. And this is actually straight out of the National Climate Assessment. It's their statement that says the intensity, frequency, and duration of North Atlantic hurricanes, as well as the frequency of strongest hurricanes, so these are category 3, 4, and 5, have all increased since the early 1980s. And hurricane intensity and rainfall are projected to increase as the climate continues to warm. Okay? So this is a graph showing you, this is actually what we call a power dissipation index. So it's a measure of the wind speed in hurricanes, and it's the cube of it, because as you go up more and more, the destructive potential of the hurricane, as you go up in wind speed, it increases not just linearly, but exponentially. And so this is the observed power dissipation index. And one thing about hurricanes, you don't hear a whole lot about them when they don't strike land. But they're still occurring out there. Okay? Always keep that in mind, but you don't really hear, last year we didn't have a whole lot that struck land. We had, one or two. Some years we get a lot, some years we don't. It just kind of depends on where they track. But the bottom line is, they're very powerful destructive storms, and it looks like they're increasing in their destructivity there. And the other part of this is, and this is the first, I guess, projection I've mentioned, is climate models don't really do a good job of modeling hurricanes because they're smaller scale storms compared to the big winter storms that you see that go across the U.S. But we have a group up in Princeton, the Geophysical Fluid Dynamics Lab, that does modeling, and they have found that when they embed a hurricane model, so you have a hurricane forecast model that does do a good job, but that's mainly for forecasting. When you embed that model into a climate model and look at what happens when you double carbon dioxide, that's where they're saying that the intensity and rainfall are projected to increase. So the question is, are we going to see more hurricanes? Well, that's an open question. We may actually see fewer hurricanes, but the ones that do occur, we think are going to be more powerful, both in terms of the amount of rain and the strength of the winds. Okay, future climate. So human-induced climate change is projected to continue and will accelerate significantly if we continue emitting greenhouse gases at the rate we currently are. I mean, I was asked today, am I an optimist about that? I am a little bit optimistic in that I think technology, who knows what's right around the corner. I don't think we're going to be burning the same amount of fossil fuels in 2075 that we currently are, but I may be wrong, and it may be due to population growth in lesser developed parts of the world. But if we continue to put out emissions of carbon dioxide and methane the way we currently are, we're going to see warming, and just how much is a little bit uncertain because we don't know what the climate sensitivity is, and that's how the climate responds to this increase in greenhouse gases. We know it's going to warm, we just don't quite know how much. And these are models from the last Intergovernmental Panel on Climate Change report, the big report, global report that's put out about every 7 years. This one came out in 2013. And just a little side note about models. So there are a number of to do a big climate model takes a lot of resources. It takes a lot of scientists, a lot of computer programmers, and supercomputing. And so there are only so many groups in the world that can kind of afford that. We have a couple of 3 or 4 groups in the US that do the big scale modeling, and there are some groups in Europe, and the Chinese are getting into it, the Japanese, and so forth. So there are only so many modeling groups, but what they do is they all get together and every 7 years come up with a set of experiments for the next Intergovernmental Panel on, or IPCC report. So that's what CMIP stands for, Coupled Model Intercomparison Project, and 5 is for the 5th assessment report. And so basically these are averaged up from all the different climate models from all the different groups around the world to give you sort of an idea of what's going to happen depending on the emission scenario. So that's what RCP stands for. RCP 8.5, which is this one right here, is our current trajectory. If we just continue emitting greenhouse gases, that's more or less what you get. And that is about how much warming you get by the end of the 21st century. Okay, that's the average of all the different models, and this is the envelope, sort of the confidence limits. And so you can get warming anywhere from about 3.5 all the way up to almost 5 degrees of warming. And 5 degrees of warming Celsius doesn't sound like a lot, but it is. RCP 2.6, which is this one down here, is kind of what I think they would be shooting for with Paris, more or less, trying to keep the warming down at about 2 degrees over pre-industrial levels. And there's actually a move afoot to put out a special report looking at what would it take to keep the warming to 1.5 degrees. Well, scientifically, that ship's already sailed because we probably already have more than enough energy in the system to exceed 1.5 degrees of warming. So that's probably more or less around 2 degrees. And then these are other scenarios depending on which one you want to look at. That's probably the one, in my mind, that may be the most realistic, that one or that one. But, I mean, who knows? You know, that's just pure speculation. But what these are is how we think emissions are going to change through the 21st century, and then you put these changes into a model, and you run the model, and you let it simulate the climate. And you don't just do it one time, you do it a number of times, so you can kind of see how the climate evolves, because the climate is chaotic, and so you change the starting conditions just a little bit, and you get a little different result at the end. But the bottom line is, if we continue on the path we're going, we're going to see at least 4 degrees of warming, or close to it. And that's going to have major impacts. Okay, this is, just for North America, this is the most extreme case. And that's one thing about the Fourth National Climate Assessment. We're trying to use what we call risk-based framing, trying to take a look at the risk as opposed to just documenting the changes in the climate and how that's going to impact things. And so this is sort of the extreme case, the riskiest case. It could be even worse, but this shows you how much warming you would get and where. And if you can see it, the darkest reds are in the highest latitudes. Okay, the darkest reds are where it's going to warm the most. And this is in Fahrenheit, since this is a US report. We're stuck in Fahrenheit and English units. But that's 15 degrees of warming up there. So you think about what that would do to the tundra and permafrost and everything else in these higher latitudes if it really does get that warm up there. And one side note, another part of that feedback I was talking about, why we expected to warm the most up there, if you look at permafrost, there's a lot of methane locked up in permafrost because it's frozen. If you begin melting that, you could begin outgassing some of that methane. Well, methane, molecule for molecule, is a much more powerful greenhouse gas than carbon dioxide is. It's just there's much less of it in the atmosphere. So keep that in mind. If you get a lot of warming up there and you begin outgassing some methane in the atmosphere, you're contributing that much more to the warming. Okay, this is winter precipitation change at the end of the 21st century from the models, and you can see we expect it to get wetter up here in the higher latitudes and then drier here in the subtropics. And these areas that are white are kind of like a transition zone. We're not exactly sure what's going on there. We don't have that much confidence in what's going on here. But we do expect it to get wetter up here. This is winter. Summer, this area the white area gets a lot larger. It's a lot more uncertain in summer. And one thing about climate models is it's very hard to model summer convective rainfall just because individual thunderstorms are not that well resolved by models, much less so than the big winter storms. But the bottom line is we think, for example, the big winter storms that come into California and the West Coast in the wintertime, the storm tracks are going to shift further north, okay, because we'll have an expansion of the tropics somewhat. And so instead of the storms coming as much down in here and giving Southern California some rain like they got this year, they'll be more prone to come in higher and higher latitudes. And so that's one reason why we would see this wetting up here and more drying down in here. Okay, just to give you a little bit of a sense for how it might impact some things, and this is something that we did a couple of years ago. This is changes in the plant hardiness zones in the U.S. over the last 10 years. Okay, you can see there's been a small shift in these different zones. And this is what we think, based on model simulations, would happen over the next 30 years. You can see some fairly large shifts across the U.S. So if you're a gardener, you might take heed, especially 30 or 40 years from now. You might be able to grow something that you can't currently grow here because it was grown further south. Projected sea level rise. This is the observed record that I showed you earlier, and these are the projections. Okay, these are anywhere from a foot to 4 feet, and the error bars actually are all the way up to almost 7 feet. Okay, and then just one note: these are mainly due to thermal expansion. As the water warms up, it expands, and then as alpine glaciers melt, that water eventually makes its way into the ocean. It doesn't really include melting a whole lot of Greenland or Antarctica, and so just keep that in mind, that if you were to actually melt all of Greenland, for example, it would go up probably about 6 meters, not 6 feet. And so that's why you've seen in the past, if you had a completely ice-free world, you'd have sea level all the way in probably to the Appalachian Mountains or close to it, close to the foothills. Okay, and this just shows you, this is for the assessment, just the areas that are really vulnerable, and not surprisingly along the coast, but Louisiana is really vulnerable, and not just New Orleans, but also because they've lost so much of their salt marsh that is a barrier for things like hurricanes as they come in. It helps dissipate some of the problems with the hurricane. But you can see, all the major urban areas are certainly vulnerable. My understanding is, I don't know how true it is, but somebody told me that New York actually already put in footers for seawalls to raise their seawalls, because if you think about Superstorm Sandy and what happened to their subway system, they got flooded, and that was, it was not a super hurricane that hit them. Okay, so just to finish up, there are positive and negative impacts. I guess if you want to call the Northwest Passage a positive, you'll be able to grow. Some people say that carbon dioxide is, and I'm not a biologist, but say that, okay, carbon dioxide is plant food, so you increase carbon dioxide, you're going to increase plant growth. Well, there's been some work that shows that as you increase it to a certain point, the nutritional value of some grains, for example, is diminished. So I don't know how true that is, but I've heard that. So there are positive and negative impacts, but in general, overall, the net impacts are likely to be negative for a variety of reasons, not the least of which is we expect to see a lot more extreme events, which by their nature are negative. And mainly it's because ecosystems and human systems are adapted to the current climate, and that's what the big issue is. I didn't show you anything really from the paleo record that shows, yes, it's been warmer than it is now, and it's been colder than it has been now. We've actually, in over the course of Earth's history, we've had an almost completely ice-free Earth and almost completely ice-covered Earth. So the climate does change on all sorts of time scales. The real issue is the fact that we're adapted to the current climate. Okay? And if it changes too rapidly, then things can adapt. And we end up with infrastructure that can't cope with extreme events and plants that can't grow where they currently are growing. So I like to finish with this one because I hear things like this a lot from different people. Being a climate scientist, as soon as somebody hears you're a climate scientist, it's either, I don't believe in global warming, or tell me about global warming. But the real point of this one, in my mind, is that even without climate change, we are vulnerable to climate and weather, and we need to adapt. We're becoming more and more vulnerable because, and a really good example is, we're building more and more people are moving into areas that are prone to hurricanes in Florida, okay, Louisiana, Mississippi, all along the East Coast. And property values are going up, people are there, and they're in harm's way. And so you have to be able to adapt to the climate, even without changes. And climate change just exacerbates the issue. That's it.
People, I will make sure the mic
Okay.
gets there.
Questions? Got another one here?
What are the issues that climate change skeptics?
Talk loud. I can repeat the question.
What are the issues that climate change skeptics raise? Is the Earth actually have these paleocycles of warming and cooling? Were the causes of warming in ancient, prehistory the same as they are now, i.e., accumulation of greenhouse gases?
No, that's a great question. So the reason why we had, so the question is, was the cause of warming for the ice ages and things like that the same as what we're currently seeing with increases in carbon dioxide? And the answer is no. The answer there is we have very long cycles with the Earth-Sun relationship called Milankovitch cycles. So we have the Earth, wish I had a globe, but anyway, the Earth is on an axis tilted like this, 23.5 degrees, okay? And so that means in the summertime, we get direct rays of the sun in the northern hemisphere. In the wintertime, it's pointed away, okay? So that's the reason why it's colder and warmer in the winter and the summer. Okay, well, that tilt goes up and down. It goes from about 20 degrees to 24 degrees over a very long period of time, and I can't remember exactly what the periods are. One's 40,000, one's 100,000, and so there's the tilt of the Earth's axis. There's the fact that the Earth's rotation, orbit around the sun, goes from elliptical to almost circular over a period of, let's say, 100,000 years. And then also, currently, the Earth's axis is pointed at the North Star. Okay? Over a long period of time, it wobbles and it's pointed in the opposite direction. Okay? So these three different, these are very long cycles, like 40, 50, 100,000 years. So when they align in certain ways, they lead to warming and cooling such that we get the ice ages and the interglacials. So that's the reason why we have those, but those are very long cycles. Those are not what we would see over the next 50 years. Okay, the reason why it's an issue over the next 50 years is that we're changing it rapidly. Okay, and we are causing it by putting carbon dioxide. Carbon dioxide over, so if you think about, say, the interglacials and the glacials, which were 10,000, 100,000 years, we also get outgassing of carbon dioxide and so you get increases and decreases in carbon dioxide in the atmosphere in response to the fact that the temperatures are changing, okay? But that's due to a natural change due to the fact that we're getting these interglacials and it's warming and then it's cooling. Oceans are warming and cooling. There's a lot of carbon dioxide dissolved in the oceans. The issue here is that we're the ones putting the carbon dioxide in there because we're burning fossil fuels. Okay, it's not sort of a natural thing.
Are there any predicting models that say if you reduce dioxide by X amount, it will have Y stabilizing effect on warming?
Well, you could do that. You can run a model, and you could reduce the amount of carbon dioxide in the atmosphere. You could see it, but so carbon dioxide has a very long residence time in the atmosphere, 100 years. So if you think of it this way, you put carbon dioxide, say here you burn in your car, that level is going to stay in the atmosphere for about 100 years. Okay, so we already have a certain amount of warming in the system. If we were to just cap emissions right now and carbon dioxide leveled off at 400 parts per million and stayed there, there's still about maybe a half a degree of warming in the system just as things catch up and stabilize. So to actually reduce temperatures, you'd have to remove carbon from the atmosphere below where it is currently at 400 parts per million. So, I mean, theoretically it could be done. There are proposals to do things like what we call geoengineering. In geoengineering, you've probably heard of putting balloons or things way up in the atmosphere to reflect incoming sunlight, or the one that I've heard most often is putting a lot of sulfate aerosols, because sulfate aerosols are little particles of sulfur up in the upper atmosphere, can reflect the incoming solar radiation and cool a climate. I showed you that with the volcanic graph, and it showed that it cooled a little bit after Mount Pinatubo went off. Well, that's a geoengineering thing, and that's a scary thing, because you start doing that, and it's going to spread all over the earth, and who knows how it could cause the monsoon to fail in India. And India says, well, Russia was putting sulfate aerosols in, causing our monsoon to fail. Who knows what could happen?
Yeah, I noticed your organization is in the Department of Commerce.
That's correct.
Does anyone calculate costs of climate change? And the second part is, do insurance companies use your data to project what they're going to have to pay out?
The answer to your first question is, yeah, there are people that do that sort of thing. I don't. I'm not an economist. But second, yes, reinsurance is all over our data. The reinsurance, Swiss Re, Munich Re, they have hazard modeling groups, and they look at hurricanes and extreme events, and they set rates based on a lot of our data.
No denialists there in the insurance industry?
I haven't met one because they pay out. Swiss Re, after a hurricane, because if you know how insurance works, you have Nationwide, who insures your home. When losses reach a certain level, say to a hurricane, reinsurance companies come in and make up the difference. And that's why they're really concerned about it, because Nationwide has so much assets. Well, Swiss Re is going to have to come in and make up the difference. And they're all over our data. They use it all the time.
What is the most compelling rationale behind the deniers? Those 2% or 3%, whatever the number is. What's the most compelling?
I would guess it's economic. Economic. It's if you see what's going on in Washington right now, it's reducing greenhouse gas emissions is a job killer. So it's economic.
To deny the science.
Well, that's the reason why if you deny the science, you don't have to worry about carbon emissions.
There's an argument they use.
Oh, the
science is rigged or hoax or whatever.
There are a lot of arguments. They look at the temperature record and they say it's not good enough. They look at models and they say they're way too sensitive. They look at the satellite temperature record. Okay, what's really interesting about that is the one at University of Alabama at Huntsville. The guy that does it is actually a bit of a denier. No, I would say he's a denier. He's a climate scientist, and he thinks that global warming is not a big deal. You aren't seeing the huge impacts right now and one of them is they keep saying that, climate models are over-projecting the warming compared to the observed record. And they didn't project the hiatus, which didn't really exist, but they don't project that natural variability in there. So there are a lot of different ways they come at it. They'll say, global warming violates the second law of thermodynamics. Okay, well, that's silly. It's been warmer. It was warmer in 1000 AD than now. Well, that's not true. They grew grapes in Greenland. How many people have heard that? Okay. Back in 1000. 1000 AD. Well, there's no evidence that they ever grew grapes there.
I don't want to be burned at the stake. I'm not a global warming denier. But several things you said. One, you said the Antarctic is losing ice and therefore increasing, yet the NASA study in 2015 says there's been no change in Arctic ice over the last 10,000 years because the amount of snow that's been put back in equals the amount of ice that's gone out. Do you have a statement?
Well, I mean, there's two ways you can look at ice. You can look at ice cover, okay, and you can look at ice mass. Okay, mass is the total amount that's there. Well, that record that I showed you was just from 2000. And prior to that, I mean, I'm not an ice expert, but I would disagree with that one.
Again, going on again, you said that there's an increase in hurricanes, and yet NOAA and NASA with GIS and IPCC AR5 and the EPA all have said there is no current evidence that there is an increase in hurricanes since the early 1900s. And you showed 1980 to 2010, but there's the same thing at the beginning of the century, and then over time, if you look at all the hurricanes and the so-called lost hurricanes and everything else, that there is no increase in hurricanes.
So what I showed you was not hurricane numbers. That was the hurricane.
No, but the thing at the top said there's an increase in hurricanes, there is an increase in
Since
extent of
1980.
hurricanes.
Yeah.
And so the implication of your slide was hurricanes are increasing because of global warming. And yet there are statements all over, even from NOAA, that that is not so.
Well, I mean, so that's straight out of the National Climate Assessment, okay? And that was looking purely at the power dissipation index. So the number of major hurricanes since 1980 where the wind speeds have been measured like that, are increasing.
It may have increased from 1980 to 2010, but it also increased from 1900 to 1920 or whatever it is.
Well, so early in the record, we don't really have a good record. Okay? We don't.
But yet, am I wrong that NOAA has said there is no increase in hurricanes since 1900?
Over that entire period, we don't have the evidence to
They
show
said there's
that.
no evidence to say that.
But for 1980, we do.
Okay.
I'm so glad you're here. I'm a doctoral student in sustainable urbanism, and the more that I'm looking into this, it's becoming clear to me that the U.S. is a leader in research on this topic, and that even our best science has lags and gaps that will be challenging as we maybe face faster changes going forward. And I wonder if you could speak a little bit to the political climate in this country right now that may be shrinking our ability rather than accelerating our ability to learn about it and to gather the data, and how this might interact with the global community. If there's, when you talk about stations, a lot of them are different. Is China going to start to pick up the gaps, or where are we globally in that?
Well, I mean, we have world-class scientists doing the work in the U.S. Yeah.
I mean, if the U.S. backs off.
Well, I mean, I don't think we're going to necessarily back off. Yeah. I mean, there are certain political policies that are changing, which is the web of the president. I mean, the president has a right to put executive orders out and make changes at how certain agencies approach things. But in terms of the fundamental science, I mean, we're still doing it. I haven't been told not to do anything. All my colleagues haven't been told to stop doing anything. There may be a slight reduction in funding, but a lot of this is predicated on budgets being passed and things like that. So I'm not overly concerned about it. The U.S. has never really, at least Congress has never really fully embraced things like the Paris Accords and things like that. So.
But would you say the U.S. is a global leader in the data science, in the science, introducing the science that we have?
No, we're still, got world-class scientists, and all the ones that I know are still working, and they're not overly concerned about it. Well, the National Center for Atmospheric Research in Boulder.
No, outside of the U.S.
Outside the U.S., well, there's the Hadley Center in Britain, Max Planck Institute in Germany. I mean, there are a lot of different ones around.
I think the concern that she's expressing, and I have it too, is should we be worried that the facts that have been transparent for many years will now be not so transparent?
So, you mean okay, well, so if you look at the science in the scientific literature, the Journal of Climate Science, I don't see that changing. Do I see some things like, the obvious, I'll be blunt, the National Climate Assessment may not be officially released by the White House when it comes out 2018. It'll get out. The information will get out. But, I mean, that's it's a report. So the National Climate Assessment is a report by the White House to Congress. And they may, right now there's no presidential science advisor. OST, the Office of Science and Technology Policy, doesn't have anybody in it. So there's nobody in there saying you can't do this or you can do that. So that could change. I mean, who knows?
24 petabytes of information somewhere. Do we have another place where that all that data?
Oh, you mean suppressing data? I don't. That's not. We're an official National Archives and Retention Records Act Center, whatever, NARA, if you've ever heard that term. And our database is always going to be there. It's always going to be available. I'm not concerned about that. There are people out there who've heard that copy a lot of stuff, just in case, but that's not going to happen. I mean,
I have just one more question. If you looked at the effects on the aquifers, there was worry the aquifers were being depleted for various reasons, irrigation and whatnot. With all that precipitation that's arriving, should we...
the aquifers? Well,
Yeah,
that's an issue. That's an issue in California in drought. If you look at the Ogallala aquifer, I mean, it's going down, down, down. I mean, that's going to be a big issue, but that's irregardless of climate change. They're just mining water because if you're mining water, you're taking out faster than it's replenished. And, aquifers. Well, so California is a good example. They're sort of out of drought right now because they had a very wet winter, but they were depleting the aquifers. They were getting land subsidence in the Central Valley because, you got all these almond trees and all these other vegetation that they're trying to keep going. And so they're getting a lot of water out of the ground. And apparently, I don't know, I think I read somewhere where there's not a whole lot of regulation in California about wells and how far you can draw down and all. So that apparently was a big issue. But aquifers are a big deal. I mean, if you look at Miami, okay, you're getting saltwater intrusion into their aquifers. So they may have water, but it may be salt water.
Well, I don't know about you, but I'm sure glad that we have scientists who are also public servants like David Easterling. Just outside and to the right in the courtyard. Feel free to stop by and say hello. And let's thank David Easterling one more time for visiting.